8.3 systems of linear equations in several variables. Today we're going to be working with a 3-variable system. So when there's 3 variables, there's 3 equations. Sometimes it'll come in the triangular form where x for a particular variable doesn't appear in the second equation, and then 2 don't appear in the third equation. So let's go ahead and start by solving this one. I'm going to go ahead and label these row 1, row 2, and row 3. This is to get us in the habit for our later sections when we are using matrices. So we see that in row 3, z equals 3. So we're going to plug row 3 into row 2. Because then we will have y plus 2 times 3 equals 5. So we get y equals -1. So we have now got z equals 3 and y equals -1. Now we need to find x. So we're going to take row 1 and we're going to put our x and y values into row 1. Or z and y values, sorry. So it goes x minus 2 times -1 minus 3 equals 1. So we get x to equal 2. We now have all 3 values, so our solution is a point on, it's a graph with 3 axes, x, y, and z. We will not be graphing these, but it goes x, comma, y, comma, z, and you get 2, -1, 3. Operations that yield an equivalent system. We can do 3 different things. We can add a non-zero multiple of one equation to another. We can apply an equation, multiply an equation by a non-zero constant, and interchange the position of 2 equations. We need these operations to change the system to an equivalent triangular system, and then use back substitution. So this is called Gaussian elimination. Gauss is a famous mathematician that started this method. So our first goal is to get down to 2 variables. So we see that row 1, x minus 2y plus 3z equals 1. Row 2, x plus 2y minus z equals 13. And row 3, 3x plus 2y minus 5z equals 3. They all have the same or opposite y coefficient. So let's eliminate y. To do that, we're going to use row 1 plus row 2. So we're going to add these 2 together to eliminate y. And we get 2x. The y's cancel. Plus 2z equals 14. Since we've already used row 1, row 2, we need to use row 3, which has a positive 2y, and we're going to add to it row 1. 3x plus 2y minus 5z equals 3. X minus 2y plus 3z equals 1. So we're going to add these 2 together. We get 4x, the y's cancel, minus 2z equals 4. So now we have 2 new equations. A and B. And those are now two variables, x and z. We need to use either substitution or elimination to solve for one variable. So I see we have a 2z and a negative 2z, so we are going to do a plus b to eliminate z. So we add these two rows together. 2x plus 4x is 6x. The z's cancel, and we get 14 plus 4 is 18. Since that's equals 18, x equals 3. Up in our notes, it said to use back substitution. Back substitution is just taking our value and throwing it into one of the last equations we use. So it doesn't matter, we could plug it into A or B. And we get 4 times 3 minus 2z equals 4. That's 12 subtracted negative 8 equals negative 2z. So z is 4. And then we had to use back substitution with x and z to find y into one of our 3 original equations. So I'm just going to take row 1, x minus 2y plus 3z equals 1. And we're going to back substitute these values in right here. 3 minus 2y plus 3 times 4 equals 1. 3 times 4 is 12 plus 3, that's 15. Negative 2y equals negative 14, so y equals 7. We have now found all 3 of our variables, so we write our solution as a point, x, y, z, 3, 7, 4. So just like we saw with linear solutions of 2 variables, there can be exactly one solution, so that means they intersect. This system can have no solution, so that makes it inconsistent. It is parallel lines. And the system can have infinitely many solutions. That means it's dependent and the lines coincide. So in our next example, we will probably have a different option, either option 2 or 3. Let's figure out what it is. We have row 1, row 2, row 3. It's going to be easier to eliminate the y's because they are multiples of one another. So let's take row 1 minus row 2 first. So we just distribute the negative, so we can just add straight across with its signs. We get negative x. The y's cancel. We get negative z equals negative 5. We use row 1 and row 2, so now we must use row 3. And we're going to subtract 2 times row 1. So we have row 3, 3x plus 4y minus 3z. Nope. Yep, that was right. Equals 5. And then we're going to take away 2 times row 1. So 2 times x, 2x, 2 times 2y is 4y. 2 times negative 2z is negative 4z. 2 times 1 is 2. Distribute the negative. So now we can add. It goes to x, the y's cancel, plus z equals 3. So now our two new equations, lines A and B, we're going to add them to eliminate x. Negative x minus z equals negative 5. X plus z equals 3. Add our two lines together, that goes to 0 plus 0 equals negative 2. 0 does not equal negative 2. This is false. And we know from 8.2 that when it is false, there are no solutions. That the lines are parallel. Our last problem of the day, row 1 is x minus y plus 5z equals negative 2. Row 2, 2x plus y plus 4z equals 2. In row 3, 2x plus 4y minus 2z equals 8. Let's eliminate the x's. That looks the easiest. So let's take row 2, subtract from it 2 of row 1. I'm doing this because we already know it had to be multiplying row 1 by 2. So let's multiply it by a negative 2. So it becomes negative 2x, positive 2y, negative 10z equals 4. Now we add it because we multiplied by a negative 2. X's cancel. We get 3y minus 6z equals 6. We use row 1 and row 2. Now we must use row 3. And let's subtract row 2 from it. And distribute the negative. We're going to get the x's to cancel. 3y, negative 6z equals 6. So now if we look at A and B, we see that they are the exact same thing. So when we subtract them to get the opposites, everything's going to cancel. We get 0 plus 0 equals 0. This is a true statement. 0 equals 0. And we know from yesterday, when it's true, it is infinitely many solutions. Graphically speaking, the lines are going to coincide.